My name is Jiri Benedikt. I'm a mathematician and associate professor at University of West Bohemia in Pilsen, Czech Republic. In my talk, I present a method how to find by computation in machine precision, a mathematically guaranteed lower and upper estimate for a principal eigenvalue for boundary value problems for differential equations, and to control the rounding errors, the so-called interval arithmetic is used. Hello, thank you for coming. Seems that you are interested in interval arithmetic, at least some of you. I will speak about a principal eigenvalue for a boundary value problem for differential equations. Why the principal eigenvalue is important? It's a value of a parameter in some system, for instance, mechanical system, which can be connected with some material constants. And this value is important because the corresponding energy functional is typically coercive, weakly coercive, for those who know what it is. Weakly coercive under this principal eigenvalue, and above the principal eigenvalue it changes and the functional is not coercive. And at the principal eigenvalue typically resonance occurs. So that's why the principal eigenvalue is important. And of course, the principal eigenvalue can be computed either by hand or in a closed form for only very simple domains, very simple equations. In a more complex situation, you can only compute some numerical approximate of the principal eigenvalue. And it's good to have a guaranteed lower and upper estimate, because if you have, for instance, a guaranteed lower estimate, then if the spectral parameter is under the guaranteed lower estimate, then it's guaranteed that the functional is, for instance, coercive. So for that, I will show a method how to use interval arithmetic to compute the guaranteed estimates. So do all of you know interval arithmetic? So just a short introduction. A silly example here. If you take this polynomial of third order, then the root of this polynomial is the number 3, which means that if I substitute 3 for x, I get 0. And if you do the same with this polynomial of order 30, and you try to substitute 1, 2, 3, 4, then you get this. So which one would you guess that it's a root? For the one which is actually a root, you get 4 million here. At 2, you get minus 8,000. So maybe this is closest to be a root, but it's wrong, of course. So if you know how the binary representation of machine numbers work, then you probably know why this error is bigger, because the powers of 3 are more rounded than powers of 2. That's simply the reason. So we can increase the precision. This was in standard machine precision with double. And we can run it. We can increase the precision, for instance, 20 digits, but we get something like this, that no significant digits can be displayed, so we still know nothing. So one of the possible things you can do is that you compute, instead of with machine numbers, you compute with intervals. So the number 3 will be represented by these two numbers. The endpoints are machine numbers, and they represent every real number in this interval. So for instance, these two machine numbers represent p. And if you perform any algebraic operations with intervals, then the result always must contain all possible results of the same algebraic operation with the real numbers in those intervals. So if I use the same polynomial here, and I substitute the intervals for x, then what these results mean, the first interval doesn't contain 0, which proves, mathematically proves, that this number 1 is not a root of this polynomial. These three contain 0, so these numbers 2, 3, 4 can be roots, maybe not, maybe yes, we don't know. Of course, from a computation with machine numbers, you can never know exactly what the result is because there is always rounding. So you can only prove, for instance, inequalities. If you want to prove that some result is, for instance, positive, then if the result is the interval that doesn't contain negative numbers, if the left endpoint is positive, then the result must be positive, and it's a proof. We can combine it with a higher precision than the machine precision. In this case, you already know that 2 and 4 are not roots, and 3 still can be a root, but we cannot know exactly from this computation. So now the boundary value problems. So I will speak about the most simple example of a boundary value problem that I know. So in one dimension, the differential operation will be minus second derivative equals lambda is the spectral parameter times u. The boundary conditions are Dirichlet boundary conditions on the interval 0, 1. And it can be easily computed by hand that eigenvalues, the definition is similar as for matrices, for instance. Eigenvalues are values of lambda such that there exists a non-trivial solution, which is an eigenfunction. So you can compute it by hand or in Mathematica that the eigenfunctions are of the form sine of t times some integer multiples of p. So the first, the smallest or principal eigenvalue is p square. We can check it here, that the principal eigenvalue is sine of p times t, and the minus second derivative is p squared times the same. So p squared is the principal eigenvalue. So of course, in this case, we don't need an estimate. We know the first eigenvalue exactly. But numerically, it's almost 10 p squared. And here you can see the principal eigenfunction. But if you take more complex situation, more dimensions with a general domain, more general differential operator, maybe even nonlinear, then it cannot be computed in a closed form. And it's enough to take a one-dimensional equation with weight here, with t plus cosine of t. I intentionally use a combination of algebraic and transcendent function because now if you try again to solve it either by hand or in Mathematica, then you get, of course, nothing. So even in this quite simple case, you can only have estimates of the principal eigenfunction. Of course, the well-known theory, Stoddem-Liouville theory, says that if the weight is a continuous positive function, then there exists a sequence of eigenvalues, and they are positive. One of them is smallest; it's the principal eigenvalue, but we cannot compute it in a closed form. So we can try to compute some estimates. So first, I will speak about upper estimate. The tool how to prove an upper estimate is to use this so-called variational characterization of the principal eigenfunction. That is minimum of this, which is called Rayleigh Quotient. And the minimum is taken over all functions from the Sobolev space W1 to 0, which means that it's 0 at the ends. And the minimum is achieved when you use for V the principal eigenfunction. We can check that if we use here the principal eigenfunction, we compute the integral of the square and of the function, then the ratio is p squared. So it's exactly the principal eigenvalue. But we can use any function from the Sobolev space, and then, of course, there is inequality that the Rayleigh quotient is bigger or equal than to the principal eigenvalue. So if we try some similar function, for instance, this quadratic function v, the blue one is the test function, and the orange one is the principal eigenfunction, so they are quite similar. And you compute the Rayleigh quotient, you get 10, which is pretty close. Now you can do the same for the non-constant weight, and you get this number, which is numerically this 7.34 something. So this is an upper estimate. So the principal eigenvalue is under this value. And now the lower estimate. So how to prove lower estimates? It can be proved using Peccone identity. I will not go into technical details here. But if you take any test function v, which now has to be C2 and positive inside 0, 1, and you find the infimum of this term, then this number is an estimate from below. It's a lower estimate. So it's clear that, again, if you use the principal eigenfunction as a test function, then the ratio is constant, and it's the first eigenvalue. So the infimum is equal to the first eigenvalue, to the principal eigenvalue. And if you use another, so we can use, again, the quadratic function, then you can easily compute by hand that the minimum is 8, and it's achieved at 1/2. Of course, 8 is more far. It's a worse estimate than the estimate from above, and it's typical that it's harder to prove some lower estimate than upper estimate. So this was for the constant weight or no weight. And we can try again the same test function with the weight. And more or less by hand, it can be computed that the minimum, the infimum is around 5.76. And now we know that the principal eigenvalue with the weight is in this interval. It's quite wide, and of course we would like to make it more narrow. So how do we do that? So one of the possibilities is to use the numerical approximation of the principal eigenfunction. So by classical shooting method, I compute the numerical approximation of the principal eigenvalue and eigenfunction. Sorry, first this. So we get this number, 7.227 something, but we don't know the error at all. We can believe that it's near, but as I showed at the beginning, we cannot know what the error is. Of course, in ND-solve, there is some accuracy goal and precision goal, but it's not guaranteed. Mark can say that it's true. So we cannot know mathematically what the error is. But what can we do? Now, this is just a plot of the numerical approximation of the principal eigenfunction. So what can we do is to use this numerical approximation, evaluate it at some points, and use them as control points of a cubic spline. Because cubic spline is C2, so it is an admissible test function. It's even in W1 to 0 if it's 0 at the end. So I define here the control points. You can see it here. For instance, with 4 subintervals, so 4 cubic functions. And I will compute the coefficients of the cubic function by hand. I will explain why. There are functions in Mathematica for that, but I'll do it by hand. So here I compute the second derivatives at the inner points, and here the coefficients. And this is the spline function. So it's C2, and it's admissible test function. And now we can try to compute an upper estimate. So let's compute. This is the Rayleigh quotient for the cubic spline. So we would expect that this is an upper estimate, but this is not correct, at least for 2 reasons. So the first one is that we had some control points. We can take them as precise numbers. Every machine number is also some real number. But for these control points, there exists some interpolation spline with some coefficients, but we computed them with roundings. So the coefficients are not exact. And if they are rounded, then of course the cubic functions are not even continuous at the control point.
Is that the floor you had on the previous slide when you defined it? You used the floor.
I used what?
Yeah, in the definition on the previous slide, you had something where you rounded to integer value.
I will get back a bit.
Well, right at the bottom.
You mean?
Right at the bottom. Right down at the bottom of the slide.
So here. Oh.
Yeah, floor n times p divided by n. Is that what you mean? In a 46.
So in what? 44, 45, 46? 46. Floor. Yes, that's because it's not rounding. It's because we have 4 cubic functions. So we compute here the index from the array of the coefficients. Yeah, so it's only for that reason. So it's no rounding. But of course, in the computation, there are roundings, there are multiplications, matrix multiplications, sums, many things. So now, how to get back? So what can we do? Of course, we can take the control points and compute the coefficients in interval arithmetics. We know interval arithmetics. So if we do this, I will represent the control points as intervals. Next, I compute in the same way the second derivatives. Yeah, should be okay. I just did something wrong here. And these are the coefficients, and they are intervals. So now the exact values of the coefficients for these control points are in these intervals. And the next is to compute the Rayleigh quotient in interval arithmetics. So it's this. And we get some interval. Here you can see that in the integration, I divided the integration not only into that n intervals, but each of those intervals into m smaller intervals, because there is that non-constant weight. So we are represented by intervals. So to make it more narrow, you can divide it. It's not the only option, but it is possible. And we get this interval with four cubic functions and 1,000 subdivisions. And we get this interval. And now the Rayleigh quotient, the exact value of the Rayleigh quotient, must be in this interval. And the Rayleigh quotient is an upper estimate. So the right endpoint of this interval must be a guaranteed upper estimate for the principal eigenvalue. So this is the estimate, the upper estimate. And this was, of course, if you want a better estimate, you can use more cubic functions. This should last some 20 or 30 seconds, and you get a better number. And you still can compare it with the numerical approximation, which is denoted by lambda e, estimated value. So let's wait 10 more seconds. You can see if I add more subdivisions, more pieces of the spline, then the interval is, in the first case, more narrow, and the second case, it shifts left.
I'm a little confused why we need the intervals. I mean, right, it's a soup overall unit, so as long as we have a function, why, you know.
Yeah, the problem is that, of course, these four cubic functions would be a function, but it wouldn't be continuous. And it's easy to find a counterexample where you get non-continuous function, you compute the Rayleigh quotient, and you get a number which is smaller than the principal eigenfunction. The continuity there is important. So for that, we have to compute the intervals here. So now you can see that the error is 10 to minus 6 times something. And now the lower estimate, the last part, which is a bit tricky. And I don't have too much time. But here, you can see what would you do if you want to find a lower estimate for this term. You just evaluate it as intervals. But what must happen? Here you see the result. The first, the principal eigenvalue is smaller, is bigger or equal to minus infinity, which is true, but it's not very useful. The reason is, of course, that you have v in the denominator, and v is 0 at the ends. And if you represent the values of this function as interval, the interval must contain 0, and it also contains negative numbers. So all possible ratios go to minus infinity. So what can we do now? We have to use a little bit different test function. Here it's what I said, that if you divide by interval containing 0, you get something from minus infinity to plus infinity. And one possible solution is to shift the test function by a positive constant, which can be done not for the upper estimate. There you need to have a function which is 0 at the endpoints. But for the lower estimate, it's enough that it's positive inside the interval, and it doesn't have to be 0 at the ends. So you can shift it. So it's better. It's not minus infinity, but it's some negative number near 0. Why? Of course, it had to happen because we have second derivative in the numerator, and it's also 0 at the endpoints. So you don't get minus infinity, but something close to 0 and negative, which is also useless. So what can we do? If you compute the spline, I finished. If you compute the spline, you can choose the second derivative at the ends. So you can choose them to be negative. So minus second derivative would be positive, and then it would be OK. So I will only try to show here a picture. So this I already showed. So this is redefining the coefficients with the shift. And here you get a lower estimate near to 7. And I will show it on the picture. So we have several parameters here. So you can see that this is the shift. So if the shift is enough that at the endpoints it doesn't go to minus infinity, now it's not minus infinity, not even at the right side. And this is the second derivative at the endpoints. So you can see what happens, that you get some estimate from below. I'll not speak about details, I don't have time. So I think I thank you for your attention for the moment. So if there is any question, 2 minutes.
So you had the closed form of the spline so that you could evaluate it with interval arithmetic. That's why you had your own definition.
Yeah, I take the control points as exact numbers, and then I must compute the coefficients in interval arithmetic. So it's not, I don't know if I can say that it's closed form, but the exact coefficients must be in those intervals, and I must compute it with them as intervals then. So all the Rayleigh quotient and also this fraction must be then computed in interval arithmetics. I wanted to show that it's much harder to get near to the, but it's clear it's the same as in the first computation that I showed. So no more questions. So thank you very much.